We were talking about ice tables, really. We did a couple more examples, I think, last time in terms of ice tables. Remember, we talked about sort of a few different ways that we can solve these problems that you will be responsible to be able to do. Pretty much we have our quadratic that we can do. And as I mentioned, you could do the quadratic on any problem if you want. If you like to do the math, you could do that. You could also, again, do sort of like a perfect square. You could also do the assumption, right? And assume that x is equal to 0. Remember that when we sort of assume that x is equal to 0, as we sort of talked about, you can really only do that based on a k value that is small. So the idea there, again, is that if the k value is small, we will not have a lot of products being made in that situation. So we will mainly have reactants when we reach equilibrium, and the change part will be relatively small or negligible, which is why you could do that assumption. When we do assume that x is equal to 0, remember, you can't take out all the x's. It is basically usually a x that you're going to subtract from a number. It could also be an x that you are going to perhaps add to a number. Those are the sort of x's that you would take out. Any x that really sort of started in the ice table with a 0 for the initial line, you would not take out. So again, because it started at 0, anything that it gains or it does change is going to be significant because basically it started with nothing. So if you get a little bit of something, that is good. Remember as well that if you do the assumption, you do need to check it. Yeah. And to check it, we are going to roll with the 5% rule here. And once again, the way that you check your assumption is once you do solve for x, you basically take that x value and you divide it by really the number you were going to, again, either subtract it from or add it to, and times it by 100%. And if it is 5% or less there, then you are good. If it is over 5%, then you do need to go and solve it some other way. And probably for our purposes there, that's going to be the quadratic, I would imagine, as the way that you would need to sort of solve it. We won't do any other successive approximation or anything like that. We're not going to do any of those type of problems. Remember that we then talked about Le Chatelier's principle, and that's an idea where we add stress to basically equilibriums. And when we do add stresses, what happens in these equilibrium reactions is they will try to adjust themselves by either going to the right, which means they'll make more products, going to the left, which means they'll make more reactants, in an effort basically to get back to equilibrium, which again is our rate of the forward and reverse direction equaling each other. So we talked about several stresses that you could do to a system. You could do something with this concentration. And when we do anything with concentration, there's really two things we could do. We could add more. And when we add more, it will always shift away from the side you added it to. We also can remove, and if we remove concentration, it will go towards the side we removed it from. So we'll shift towards the side we removed. The idea really in both of these cases, and really all the cases of Le Chatelier's principle, as we talked about, is essentially what's going to happen is it's going to cause either the forward reaction to occur or really sort of initiate the reverse reaction in all these cases. So in the case, for example, if we added more products, what will happen is we now have more products than reactants, and that's going to cause the reverse reaction to occur. And since we added more products, the reverse reaction will kick off and it will actually shift away from the side we added it to in terms of the equation. And same thing would happen, obviously, if we added more reactants. We would then have more reactants and products, and what that's going to do is cause the forward direction basically to occur, and again, it would shift away from it. The opposite is sort of true when we remove something, in a sense. If we remove more products, what that essentially does is it then allows you actually to have more reactants and products at that point, and that also is going to cause the forward direction to occur and head towards the product side. And same thing here, if you took out some products, you're going to have more, I'm sorry, took out some reactants, you'll have more products that will cause the reverse reaction to occur. And again, that's why it goes towards the side you remove it from. If you just want to easily remember that, again, like I said before, you can think of it like you made a big hole on that side and it's got to fill the hole, so it'll go towards, the hole to fill it. We also talked about volume and pressure, which oftentimes are sort of tied together. And again, as the pressure increases, that's usually a result of the volume decreasing. And sort of the change that's happening here again is the pressure is going up. We want to kind of bring it back down. So we're going to go to the side with the least number of gas molecules. And obviously that is reaction dependent as to which side that is, left or right. If we do the opposite, we lower the pressure, we will see, not that, we will see an increase in the volume. And again, here, what's going to happen is the change is happening as the pressure is dropping. We kind of want to bring the pressure back up. So we'll go to the side with the more gas molecules. Again, personally, I usually just think pressure, volume, and all that in terms of thinking about the volume. It's basically the same answer as the volume. So if you have a smaller volume, less gas molecules. You have a larger volume, more gas molecules is the way that you want to go on that. We then talked about temperature as well. And remember, temperatures really works the same as concentration. The difference, though, is it's really dependent on whether it is a exothermic reaction or an endothermic reaction. And exothermic heat and energy is released, endothermic heat and energy is absorbed. And in this situation, most of the time, the way that is represented to you is with the delta H, which is the change in enthalpy value. And if that is a negative value, it really doesn't matter the number, but if the sign's negative, it will be exothermic. And if the delta H is a positive number, it will be an endothermic reaction. In terms of how we think about heat in this situation, or temperature in a sense, is if it's exothermic, we think of heat as being a product, again, like it's being given off. So what that would mean in an exothermic reaction, if you increase the temperature, it would shift to the left away from it. And if you decrease the temperature in an exothermic reaction, then it would come to the right-hand side there towards the product side. And the opposite would be true, obviously, with an endothermic. Heat is considered a reactant in that case. And same idea here, if we increase the temperature of an endothermic reaction, we're going to end up with the reaction shifting to the right, away from the reactant side. And if we decrease the temperature, put everybody on ice, it's going to go to the left. Lastly, we talked about a catalyst, I think. And a catalyst, again, is not a reactant, not a product. It does not get used up in a chemical reaction. It's there really just to facilitate the reaction occurring a lot more efficiently. And in terms of sort of shifting to the left, shifting to right, it really will have no effect on it. So have no change that will occur. You'll get there quicker, but it will not change anything. That's one of the ways, as we talked about, that you can kind of get a no change in the situation. Another way that we also talked about was the idea with the gas molecules. So obviously, if you got an equal number of gas molecules on each side, there is no more or less side. And that's another way that you could kind of get a no change situation. And also occasionally like a noble gas might pop in there as well, which are chemically inert, won't do too much. Questions on any of that stuff there? All right, so just do a few more here. Examples. Obviously, this is stuff we've been talking about there. Concentration shifts away, goes towards it. Temperature works the same way, depending on whether it is exothermic or endothermic. Remember, again, as we've been talking about, temperature, again, is the only thing that will actually change the value as well of the equilibrium constant. Pressure, again, more or less gas molecules, depending on whether the pressure is increasing or decreasing. All right, so let's just say we have this one, and for fun, we'll just say the delta H is negative. Maybe it is, maybe it's not. All right, so for each of these, will this go to the left? Will this go to the right? Will there be no change? If we do the following things, let's add some H2. We're going to lower the temperature. We're going to remove NH3. We're going to increase the volume. We're going to add N2, and we're going to increase the pressure. So for each of these cases, would we expect it to shift to the right, to the left, or will there be no change? So take a couple minutes there and see what you come up with. Okay, let's take a look. So in this case, we're going to add more N2, or H2. H2 is over here on our reactant side. So again, that's going to shift away from the side we added it to. So it should go toward the product side. That's going to kick off, once again, the forward direction in this situation. We're going to lower the temperature. So when we see a delta H that's negative, that is a exothermic process. And exothermic means that really we consider heat a product in this case. And in this case, as we're going to lower it, that would be like removing the heat and temperature on a product side. And that's going to cause it to shift towards the product side in that particular case. We're going to remove NH3. So once again, we're going to remove NH3, which means really we got more reactants than products. So that's going to cause the forward direction to occur, and it's going to cause it to shift towards the side that we removed it from. We're going to increase the volume. That also would mean, by the way, that the pressure would be dropping. And because we now have a larger volume, we do need more gas molecules in there to kind of bring the pressure back up as well. And in this case, we have 4 gas molecules, and here we have 2. So in this case, we would shift to the left in that case. Lastly, here we're adding N2, which is a reactant. That's going to cause more reactants than products. Going to cause that forward direction to occur and shift away from the side we added it to. And increasing the pressure here, we will end up with a smaller volume. So once again, in that smaller volume, we need less gas molecules, and it should shift to the right in this case. Any questions on any of those there? All right, one last one here. Let's do increase pressure, add a catalyst. Let's do decrease temperature. Let's add O2. Let's remove NO. All right, so here we have increased the pressure. That again relates really to a smaller volume. So once again, in the smaller volume, we want actually less gas molecules to fill that up. In this case here, we got 2 gas molecules, and over here it kind of looks like 2 as well. So that's going to be a no change situation in this case. Again, we got equal number of gas molecules on each side, so there really is no more or less. While we're at it, adding a catalyst will also cause really no change to occur in this case. So let's go to decrease our temperature. This case is endothermic. That means that heat would be considered a reactant. And again, our delta H value would be positive probably in that case. And because of that, we're going to decrease the temperature. That would be like removing our reactants. That is going to cause it to shift towards the side that we removed it from, and it should go to the left. Lastly, here we're going to add some O2, and that's going to cause it to shift away to our product side, again, kicking off that forward direction and removing our NO, really meaning, once again, we got really more reactants than products, causing the forward reaction to occur and is going to head towards our product side in this case. Any questions on any of those? Yes? No, it really won't. It really won't shift the equilibrium or anything like that. You just kind of get there quicker. It'll just do that. So it really won't cause it to go one way or the other. Other questions? All right. Dare I say that is, chapter 12? That sounds good. All right. We are quizzing on chapter 12 on Thursday. I seem to vaguely remember something like that. Now, if I just remember to write the quiz, that would probably be good too, I imagine. We'll see how that goes. I suppose, right? All right. Either it'll be a good Thursday or a bad Thursday. All right, then we are off to the next chapter because we should do something, I suppose. There we go. All right, so we're going to talk about acids and bases in this chapter. And since we're talking about acids, is something that you probably named before. So just a reminder before we get too far into it about how we name acids. Give you the Cliff Note version here. So when you go to name acids, it really involves whether or not you've got oxygen, right? So oxygen is really the main thing there. And if you do not have oxygen, no oxygen, we do start the name with hydro, and then it's something ic acid. So HCl. And typically acids have the aqueous symbol next to them to imply that they're in solution. That would be hydrochloric is the missing part there. So not with a C, that's a hydrochloric acid. We have HBr, once again, no oxygen, so that would be hydrobromic acid. Now, if your acid does have oxygen, it most likely will contain one of those polyatomic ions that everybody loves, which ends in 8 or ite typically. And if your polyatomic ion ends in 8, your acid is something ic acid. So HNO3. That is oxygen. NO3 is nitrate. So that's going to be nitric acid. I'll go up on top here. H2SO4. SO4 is sulfate, and that is sulfuric acid. Pretty much for all acids, the cation is H plus, right? So that's pretty much your cation there for all acids. If your polyatomic ion ends in an orange, so if it ends in, go here maybe. If it ends in ite, your polyatomic ion is going to be something OUS acid. So HNO2. NO2 is nitrite. This would be nitrous acid. So it's good to know how to name acids, right? So you just go like that thing there. Like, for example, today we're playing with 12 molar hydrochloric acid, quite strong. Yes, so strong acid. We want to be careful a little later on today. All right, so let's get into acid and bases. That's an orange over my acid sign there. So acids, they do have a sour taste. Vinegar, for example, is basically acetic acid is the main component of that. Citric fruits have citric acid. Acids react with certain metals to produce hydrogen gas in a single replacement reaction. For example, like some zinc and some hydrochloric acid. The zinc will come in and kick out the hydrogen. The hydrogen gas would then be formed, make a little zinc chloride action with it. Put a little 2 there, like I'm in chemistry class. There we go. And remember, in these sort of single replacement reactions, whatever's coming in needs to be more reactive when it's replaced in order for that reaction to take place. They also react with carbonates and bicarbonates to produce carbon dioxide via something like this, like hydrochloric acid, and maybe like a little sodium carbonate. And again, this is going to actually be a double displacement reaction happening, making some sodium chloride and a little H2CO3. H2CO3 is carbonic acid, and that very quickly decomposes into your CO2 and water, basically. Yeah. Plop, plop, fizz, fizz, a little 2 there and a little 2 there, and I'm out of 2s, I think, at that point. There we go. Bases, on the other hand, they feel very slippery. A lot of soaps are bases. Um, Drain cleaner, that type of stuff are bases as well. A lot of our bases or strong bases do come from group 1 or 2 on the periodic table. That's where we have our alkali metals and our alkaline earth metals. The word alkaline means basic, so a lot of those guys with water is how you kind of produce a lot of the strong bases coming down from like lithium, sodium, potassium, hanging right at calcium, strontium, the barium. That's where a lot of strong bases sort of come from. Now, sort of an early definition of acid and bases was one done by Arrhenius. It's the definition, basic definition of an acid, which is something that will produce H plus ions. That's what is sometimes referred to as hydrogen ions. H plus is also sometimes referred to, as we'll see shortly, as a proton as well. And that is because hydrogen has 1 proton, 1 electron, and no neutrons. So in order to become positively charged, it had to lose an electron, which leaves it just a proton left over, which is why I sometimes refer to that. Also, H3O plus, that is the hydronium ion. And for all intents purposes, when you're doing acid-base chemistry, pretty much H plus and H3O plus, pretty much the same deal. So you could use H plus, you could use H3O plus. I personally use H plus most of the time, but books and stuff like to use H3O plus. You can use it interchangeable in formulas. You can also use it interchangeable in reactions as well. So, you know, you can kind of pretty much anywhere I put an H plus, you can almost put an H3O plus and basically be the same thing. It's really the acid part. And the difference as to why, for example, you might have one versus the other is if we look at actually what's up here. What we're looking at in this reaction here with the hydrochloric acid is basically the hydrochloric acid dissolving in water and breaking apart into its ions. Now, that is a perfectly fine representation of what is going on. And when you do that, what's actually happening is, again, this is going to actually send the H plus over to the water. And that is how we're going to generate our H3O plus. You can just as correctly write this reaction, which is really just the dissociation of this strong acid, by just simply writing it like this without the water included. And you will get this reaction. And again, that H plus and that H3O plus are basically the same thing. So for acids, particularly if you kind of include the water to show it dissociating or breaking apart in water in the actual equation, you should produce H3O plus. If you just kind of show the acid breaking apart into its ions, like H plus and whatever it is, then you will not have the H3O plus. So either way is okay. And again, they're basically the same thing. They basically tell you an acid's happening. Now, the definition of an Arrhenius base is a substance that's able to produce hydroxide in solution. And when we talk about the ability to produce H plus or hydroxide in a solution, what we're talking about is the ability really to release those things so that they are freely floating around in the solution, the H plus. And the same thing with the hydroxide. You know, they're not really with anybody else. They're just kind of floating around in the solution. And that is what we see here with ammonia. Ammonia is actually a weak base, as we'll talk about. It does not actually have hydroxide, for example, on it. But what it's able to do, for example, as we will see many times as we go through these chapters, it is able to actually pull an H plus from water. The result of that is it is able to produce basically hydroxide on the product side and is considered a base because it's able to do that. Now, there's definitely stronger bases like the popular sodium hydroxide, which pretty much just needs to go for a swim and it's going to break apart there into Na plus and OH minus, and it's also going to produce hydroxide. So a lot of strong bases, which come from group 1 and 2 on the periodic table, will kind of carry hydroxide with them. And that's really why they're strong bases, because frankly, they just go for a swim and it's going to produce the hydroxide. Something like ammonia, which is a weak base, it's got to go find some water, do a little reaction to kind of produce that hydroxide. So it's not going to produce as much in a very fast period of time as, say, something like sodium hydroxide that just simply has to go into like the beaker, the solution, and stuff like that. Any questions on that there? Now, that was a good definition of an acid and base, except that he did a lot of work with really just hydroxide as its base. And a more general definition of acid and bases is the Bronsted-Lowry definition. I'm not sure where Lowry's name went, but we'll put it back in there for good purposes. The Bronsted-Lowry definition of an acid and base is an acid is a proton donor. So that is something that will give away an H plus. And that's really an important part of it. People oftentimes focus only on the H and don't realize there is a plus that goes with that. And that does have an effect on things. So obviously, if you gain the H plus, you now become one more positive because you gained the plus charge. If you lose the H plus, you become one more negative because you lost basically a proton, right? So you're one more negative. So you got to make sure you take into account how the charges of everything changes as they gain or lose that. And again, sometimes people just focus on the hydrogen being gained or lost rather than what happens with the overall charge. A Bronsted-Lowry base is a proton donor. So once again, it's going to accept our H plus. So in this example that we saw a second ago with the ammonia, ammonia here is actually acting as the base because it's going to accept an H plus here from the water, which means in this case, water is actually acting as the acid. So water is acting as the acid in this case. And the result of the NH4, NH3 gaining the H plus is it will become NH4 plus on the product side, which is a polyatomic ion. And the OH minus will be produced on the product side as a result of the water giving away its H plus. A consequence of the Bronsted-Lowry definition is they will actually create partners on the other side of the arrow. So the base on one side of the arrow, its partner on the other will be what is known as the conjugate acid. And the acid on one side will have a partner on the other side, which is known as its conjugate base. Now, what is the only difference that you could have between, say, a base and a conjugate acid or an acid and a conjugate base? It is this guy right here. It is the 1H plus. So it can only be a difference of 1H plus in order for something to be partners. If you have a difference that is greater than 1H plus, then they are not conjugate acid base pairs. They are not really partners in that sense. That is the only difference that you could have. Questions on that there? So let's take a look here, and for each of these, decide which one is a conjugate acid base pair. So take a few moments, see which one of these groupings are partners and pairs. Okay, so let's take a look. So one of the things you want to think about is whether these are partners or pairs. And the one thing that you want to think about is pretty much, is this the only difference? So once again, in order for them to be pairs, that should be the only difference. So if we look obviously here at HCl and ClO minus, I don't know why they write that way. Obviously the difference here is an H plus, but we also have a difference of an oxygen that this one obviously doesn't have. So that would mean that these guys would not be pairs, as again, there's more than just an H plus difference between them. How about H2SO4 and SO4 2 minus? Are they partners or pairs, these one? The answer is they are not. The difference between this is actually two H pluses. So they are not pairs. Once again, it can only be an H plus difference. NH4 plus and NH3, these guys are a pair, as the only difference between them is an H plus. You could either take the H plus off of that guy and you end up with this guy, or add it to the guy on the right, you get the guy on the left. So that is a winner. H3O plus and OH minus, are they partners? The difference here is actually two H pluses as well, I believe. So that would not be a partner. So it looks like 3 is actually the only partner that there is. By the way, you may be wondering why these guys, once again, are not partners, other than the fact that I said it's more than one H plus. They are related to each other, obviously, because they both have sulfate in there, but they are not partners in terms of conjugate acid-base pairs. When we talk about hydrogens and all that, hydrogens actually, for example, come off acids when you have more than one hydrogen, like a diprotic acid or a triprotic acid, which would have 3 hydrogens versus a diprotic acid that has 2 hydrogens. They come off actually one at a time in a stepwise fashion. So for example, if you took sulfuric acid, that should be more like a one-way error on that guy. We'll have HSO4 minus, and then we'll have H plus, basically. And then what will happen is that HSO4 minus will come and break apart into SO4 2 minus and release a second hydrogen in this case. So when we look at sort of partners or pairs in this case, this guy here, H2SO4 and HSO4 2 minus, these guys are pairs with each other, as the only difference is one H plus. The HSO4 minus actually and the sulfate are also pairs with each other, as they are only one H plus. But jumping from here directly to here, that would not be a pair again, because it's basically a 2 hydrogen difference between them. Any questions on that there? Okay. So for this guy here, we're looking, what is the formula of the conjugate acid in this case? So what should the formula of the conjugate acid be if we started with this guy here? Okay, so what we want to think about in this case is the relationship that we talked about, where we have an acid and a base. And on the other side, we basically have our conjugate base and our conjugate acid. And remember that our acid and our base go together, our base and our conjugate acid go together. So in this case, we actually have C6H5NH2, and we want the conjugate acid. So what you want to think about in this case is, what is this thing that you're looking at? And since we want to end up at the conjugate acid spot, it has to come all the way back this way, and it should tell you that what you're looking at is a base. And pretty much what you need to do at that point is just the definition of a Bronsted-Lowry base, which means it will actually accept an H plus. So we actually want to put the H plus on in this case, and we should end up with C6H5NH3 Na plus would be our answer. Looks like number 2, I think. Yeah, so 2 looks like a winner in that case. Question on that one there. Now, if we had, say, something like our HCO3 minus, and we want the conjugate acid, and we also want the conjugate base. So starting with this guy, in both cases, what would be the conjugate acid and the conjugate base? Okay, so once again here, pretty much we hopefully should know we need to do something with an H plus, so either put it on or take it off, which is pretty much most people struggle as to like what to do with it, I suppose. So we'll start here, and we will do perhaps the conjugate base first. So if I want to do the conjugate base and end up at the conjugate base, so we want to kind of think about it backwards. So if I want to end up at the conjugate base, that means in this particular case, what I'm looking at is going to act as an acid. And the definition of acid is going to get rid of basically an H plus, and that will give us CO3 2 minus in this particular case. Now, if I want to do our conjugate acid, like in the problem we just did, if we kind of go backwards, that takes us back to our base once again. And that means we're going to actually add in the H plus, and that will give us a little carbonic acid in that case. Any questions on either of those? Yeah. So sometimes in these type of problems, we're asked to either write the formula of the conjugate acid or conjugate base. You want to kind of think about it backwards, if you will, where it came from, and then all you have to determine is, was it an acid or a base, and follow the definition. Yeah. It does. As you can see here, it started with a -1 overcharge, and we're adding an H plus, so +1 and -1 ends up being 0 at that case, so it actually went down. It became one more positive, basically, because you added it. And the same thing on this side here as well. We actually lost an H plus, so when we lose an H plus, we actually become one more negative. So we started at -1, and we ended at -2 in this case, yeah. Yep, other questions? Now, another thing that we may notice there is this guy here clearly can act as both an acid or a base, and that is what is known as being amphoteric. Amphoteric substances can act as an acid or a base, and typically things like this guy here with the has a hydrogen and also has a negative charge. A lot of those guys have the ability to act as an acid or a base because they have a hydrogen, they have one to give. And because they have that one to give and they have that negative charge, they could actually gain a hydrogen in most cases. So HCO3 minus, actually SO4 minus that we were looking at on this page, this guy as well could act as an acid or base depending on which way you go. If he continues to donate its H plus, it's going to go that way. If he accepts an H plus, he'll go back that way. So again, it can act as an acid or base. Also, our good friend water can do that as well. Water could give out an H plus, or it can accept an H plus. So water also is amphoteric and can basically do both. Any questions on conjugate acid-base pairs? Obviously, you need to be able to write the formulas correctly for those and identify them as obviously a conjugate acid, conjugate base, and an acid and base. Any questions? Yeah. So speaking of water, water, as I just mentioned, can also act as an acid or a base. And water, because of that, actually just reacts with itself because one water could act as an acid, one water could act as a base. And in this case, we're going to basically take an H plus off of this guy. So we'll have our acid, one of these here, and this will be our base. And again, we'll get our conjugate pairs on the other side. This is constantly what's sort of happening with water. It actually will set up an equilibrium. You guys can see up here, H plus, H water goes to H plus and OH minus. Once again, you'll sometimes see this written H2O goes to H3O plus and OH minus as well. So again, it could be either one and maybe balance two waters basically in that particular case. So kind of the same reaction. It is an equilibrium, which does give us, believe it or not, an equilibrium constant. And that is what is known as Kw. And Kw is the equilibrium constant for basically the ionization of water. And once again here, water is not going to be included in the equilibrium expression because it is a liquid. So basically here it is just the products. And our real Kw value is right there. Kw is equal to H plus times the OH minus concentration. A reminder that when you do see these brackets, it is concentration, right? And again, usually that is molarity that we're talking about in that situation. It does equal an actual number. It does equal 1 times 10 to the minus 14. And this is one of many that, again, you will sometimes see that H3O plus written instead of H plus. and it again is the same thing. And whichever one you prefer, I usually again will use H plus, but if you want to use H3O plus, not a big deal. That is the value of Kw, and I would say in most cases, if you need the value of Kw, that would be the number you use. A reminder though, as we talked about in the previous chapter, Kw is an equilibrium constant that we could add to our list of Kc and Kp. That's Kw, ever-growing list. It will also be affected by temperature, right? Because it is an equilibrium constant. So if by some chance you come across a problem where they give you a weird temperature or something like that, they may also give you a different value for Kw because it will change with temperature. But I would say probably 99 times out of 100, that's going to be obviously the number you're going to roll with, even more than that probably. But again, if you do come across it, it may also reference a different value if the temperature is different than what we see here at 25 degrees. So, but pretty much it's a constant number in most situations that you want to use. What can we do with that? Well, frankly, the H plus is really the acid part of the solution, and the OH minus is really the base part of the solution. So we could actually use this to calculate the concentration of the H plus or the OH minus if you know one or the other. And you can actually compare the values. So if you calculate the H plus concentration, which is the acid concentration, and it's equal to the OH minus concentration, which is the base concentration, your acid and base equal each other, you basically have a neutral solution. By the way, at that point, it's going to equal basically 1 times 10 to the minus 7 molar. Each of those will be what it will equal. If you calculate the H plus concentration is actually larger than the OH minus concentration, the H plus concentration, which is the acid part, is bigger than the base part, so your solution will be acidic. And if you calculate that the OH minus concentration, which is the hydroxide concentration, is larger than your H plus concentration, then your solution will be basic. These are calculations that will involve exponents, so you definitely, again, want to make sure you are using your exponent button on your calculator so that everything gets punched in correctly. So let's try one here. So what is the concentration of OH minus in an HCl solution that has a hydrogen ion, Kw expression, which is our H plus concentration, which is the acid part, times the OH minus concentration, which is the base part, equals 1 times 10 to the minus 14. The good news is it's the same rearrangement, regardless of what you're solving for. So the OH minus will equal 1 times 10 to the minus 14 divided by our H plus concentration. And that's going to give us 1 times 10 to the minus 14 divided by 1.3. And in this case, looks like perhaps 7.7 times 10 to the minus 15. And this does need units of molarity to match the other molarity there. Any questions on that one there? Yeah. It is. You could calculate the pH from these things in about 4 slides, maybe 5 slides. Yeah, so we'll get there shortly. Is this acidic, basic, or neutral, this one? It is acidic. If we compare the H plus concentration to the OH minus concentration, obviously that one is larger, so it would be acidic. By the way, just for future reference, if you're asked that question, is it acidic, basic, or neutral, there's just one answer for that, not multiples. So sometimes people go, it's acidic and also basic at the same time. I've never had anybody do all three, though. I've never had anybody say acidic, basic, and neutral at the same time, but definitely I've had acidic and basic. So we'll talk about why that probably happens a little bit, but we'll get there. But just one answer for that. All right, let's try this one here. We got H plus concentration 1.2 times 10 to the minus 6. What would be the hydroxide concentration? And is it, again, acidic, basic, or neutral? Once again here, we're going to use our Kw expression, our H plus concentration times our OH minus concentration equals 1 times 10 to the minus 14. In this case, we are looking for the hydroxide concentration, going to give us a 1.0 times 10 to the minus 14 divided by the H plus concentration, 1.2 times 10 to the minus 6. Again, for reminder's sake there, going to hit a 1, your exponent button. your negative button, and 14, a little divide button, perhaps a 1.2, an exponent button, a negative button, and a 6, and perhaps an equals button. And if you do all that good stuff, you should get 8.3 times 10 to the minus 9 molar, are on most people's calculators a bunch of zeros with like an 8 at the end, right? Because you ran out of room, basically. Yeah. So probably like 8 zeros and an 8 at the end, which is fine. 8.3 if you had it in scientific notation, but again, if you had 8 times 10 to minus 9, it would be okay as well. In this case, we want to compare the H plus concentration to the OH minus concentration. And in this particular case, which one is larger? It is the hydrogen concentration, right? It is larger. The hydrogen concentration is to the minus 6, and our hydroxide is to the minus 10. Remember that when you're comparing negative exponents, the smaller negative exponent is actually the larger number. And that is for this reason, right? 1.2 times 10 to the minus 6 means going 6 places that way and putting zeros. 8.3 times 10 to the minus 9 means I'm going 9 places that way and putting zeros, which is going to make it a much smaller number. So when you're comparing the negative exponents, smaller negative exponent actually is the larger number of the two. Question on that one there. So that would be 4. Looks like a winner, I think, on that one. All right. So let's talk a little about pH and the pH scale. pH is a measure of acidity. And we do use the pH scale to help us determine whether or not something is acidic, basic, or neutral. The pH scale does run from 0 to 7 to 14. Below 7 is acidic. Exactly. Above 7 is basic. At 7 is neutral. And 7 is sort of your neutral point there. As you go from 7 towards 0, you become more acidic. As you go from 7 towards 14, you become more basic. We are going to use 7 as our neutral point. So if it's not 7, it's a little above 7 or a little below 7, then it's going to be slightly acidic or slightly basic. Because technically speaking, neutral is when those concentrations equal each other, and that would give you a pH of 7. So if it's not like super close to 7, like 6.99 or something like that, then we're going to consider it either acidic or basic slightly in either direction. So a neutral solution would have an H plus concentration that equals an OH minus concentration. And as I mentioned before, that would mean that the H plus concentration is actually 1 times 10 to the minus 7. And that would give you a pH of 7. If it's acidic, then as we talked about, we have a higher H plus concentration and OH minus concentration. And that would result in a pH that is less than 7. And if it's basic, we would have a greater hydroxide concentration, OH minus, than H plus, and that would get you a higher pH than 7 in that particular case. Couple of important relationships, by the way, as the H plus concentration increases, the OH minus concentration goes down, and they run opposite of each other. So as the H plus concentration decreases, the OH minus concentration would increase. So H plus and OH minus kind of balance each other in that sense. One goes up, one goes down. They kind of go like that. And as the H plus concentration decreases, we will see an increase in the pH. And that is because as the H plus concentration goes down, the OH minus concentration goes up. So it has more basic than acidic, and we'll get a higher pH. And vice versa, obviously, if we have a greater H plus concentration, we would start to see again our pH drop. To actually calculate the pH, we use this equation here. The pH is equal to negative log of the H plus concentration. Once again, this is one of those formulas that you can substitute the H plus for H3O plus. It again is the same thing. Now, if you have a calculator that's a non-display calculator versus a display calculator, you will punch this in differently, this formula and some other formulas we're going to see. So if you have a display calculator, you're basically going to punch it in exactly the way it is. You're going to hit the negative button, you're going to hit the log button, and you're going to put the number in probably with your exponent. If you have a non-display calculator, this formula here and some others, you actually need to work backwards, which means you need to actually start with the number. You then need to hit the log button, and you then need to hit the negative button there to turn it positive. So display, you go just the way it's written. Non-display, you go that way. If you're not sure what calculator I'm talking about, you just hit the log button. And if your calculator says log to you, congratulations, you have a display calculator. If you hit the log button and it says error, congratulations, you have a non-display calculator. That is a quick way to figure out whether you have it or not. So if it says log, go forward. If it says error when you hit the log button by itself, you need to go backwards, basically. Yeah. Any questions on that there? I think that's right. Now, when we do pH here, we also want to talk about significant figures with pH. So maybe I'll go this way and use some of this page here. So pH and values like pH and sig figs. So when you calculate a value like pH or a similar type of value, the number of significant figures in the concentration value will equal the number of decimal places you take the pH to. So for example, if you had an H plus concentration of 1 times 10 to the minus 5 molar, why don't you calculate the pH of it? Okay, so you should have on your screen, I'll draw your screen up here. You probably should have that staring at you, I hope, on your screen. So you should get a 5 on your calculator screen there. Little pH is equal to negative log of 1 times 10 to the minus 5. And that is going to give you a 5. Now, when we go to report this as our pH value, we have options. Do I go 5? Do I go 5.0, 5.00? Which one would be the proper way to report this one? So 5.0, any other guesses? Everybody agrees? No? No? Yes? So when we look at the concentration value, which is over here, how many significant figures does this have? 2 significant figures in the concentration gives me not 2 significant figures in the pH. Gives me 2 decimal places, yeah? So we're going from significant figures to decimal places when we're calculating something like pH. By the way, if you're going backwards, which we will go backwards, and you have decimal places to significant figures in the concentration. So it goes both ways, depending on whichever way you're going. But again, concentration, significant figures, decimal places, and pH. So not sig figs to sig figs in this case. So by the way, that would be acidic, basic, or neutral? That would be acidic. Yeah, sounds good. All right. Question on that there. Now, in addition to pH, there are some other scales similar to it. And one such scale measures actually the hydroxide concentration, and that's known as the pOH. By the way, the names tell you exactly what you need to calculate those things. So if you're calculating the pH, you need the H plus concentration. And if you're calculating the pOH, you need the OH minus concentration or the hydroxide concentration. The pOH there is negative log of the OH minus concentration. I'll slap my pH equation in there with it. Now, why you might want to calculate the pOH versus the pH, besides that maybe they ask you that, is there is a nice relationship between pH and pOH. And that is if you take the pH plus the pOH, it equals 14. And that means that, for example, if you wanted the pH of a solution, but you were given the hydroxide concentration, you could calculate the pOH and then take 14 minus it, and you'll have the pH really quick. So you could do that really quick. By the way, you could also, if you wanted to, still use our KW as well. So, if you wanted to, and you're given the hydroxide concentration, you could use KW like we did before and get the H plus concentration, then go into the pH. It's your call, whichever way you want to do it. Should give you the same as well. So the pH and the pOH are different. Again, one is measuring the H plus concentration in the solution. One is measuring the hydroxide concentration. Now, I said earlier, sometimes people would give the answer of it is acidic and basic at the same time. And this is why people will do that sometimes, because they will calculate the pH and also calculate the pOH and go, cool, this is, like 9.0. And then this pOH there is like 5, I guess that would be there. And they go, okay, cool. Like the pH there is above 7, so it's basic. And then they go, cool, the pOH is less than 7, so it's acidic. Yeah. But that's the same solution, by the way. Yeah. So don't do that. Fight that urge to do that. Again, only one answer, regardless of which one you calculate, right? I personally would recommend that you probably look at the pH, because that is the scale most people have in their head. The pH scale is obviously what we just talked about a second ago, 0, 7, 14, acidic, basic, and neutral. The pOH scale also is 0, 7, and 14, but it is opposite. That is basic, and this is acidic. Yeah. So if you have a high pH, you will have a low pOH, and vice versa. But again, most people have this scale in their head, so you should always just probably look at the pH and make the determination if it's acidic, basic, or neutral based off of that. Question on that there. Yeah.
Scale I have seen that it was already that you allow say this pH scale it's acidic rather be converted than said based on the pH scale.
Truthfully, if it was just a question of is it acidic, basic, or neutral, and it wouldn't matter as long as you did it correctly, I suppose. Now, I would say usually you would be using a lot of times the pOH to probably get to the pH in a lot of cases. So in a calculation, obviously you would need to calculate it. But if it's just a straight up question of is it acidic, basic, or neutral, if you remember it correctly, you could do it that way. Yep. Other questions? Now, why we have this other slide here. In addition, you can, if you have the pH, for example, from the pH itself, if you're actually given the pH value, you can get the H plus concentration directly from it. And you could get that by taking the H plus is equal to the inverse log of the negative pH. I would say on most people's calculators, when you do the inverse log, it will usually pop you up a 10 and a caret, usually on your calculator, and a negative pH. And you could also, if you have the pOH directly from that, you can get the hydroxide concentration. So the hydroxide concentration would be pretty much the same calculation, the inverse log of the negative pOH. And once again, that usually will put up a 10 and a caret, negative pOH. Once again, to get to the inverse log on most people's calculator, usually the second button, the shift button there, top left, and right above the log button is usually see this. That is what a lot of people commonly use for a very long time to do exponents incorrectly. So this is what you should use it for, maybe something like that. So that is how you get to the inverse log. By the way, just like the pH equation and the pOH equation, depending on your calculator, display or non-display as to how you need to punch that in. If you have a display calculator and you're going to do this guy, you would do the maybe the second button and the log to get you to the inverse log. And then you would do your negative button and your number. If you have a non-display calculator, you actually got to start with the number. You then need to make it negative. You then need to do the second button probably and the log button. So again, you kind of have to work backwards if you have a non-display calculator when you punch these in. And again, if you have a display calculator, you could just go kind of forward in terms of the way you punch it in. Any questions on that there? All right, so we'll lay it up there, I think, for today.